We have discussed so far what happens if we've got a reaction. For example, A is consumed. So A is the reactant. And we said we can write the rate equation. So the rate for this would be actually a change in the concentration of A per change in time. And we said this is positive or negative if it's consumed. It's negative, thank you, yes, excellent. Minus K times, let's make that a general thing, concentration of A to the power of, let's say, M. And of course, this M is the order of the reaction, and the order of the reaction is just simply a mathematical concept. And M can be any number, whatever makes this equation work. Last week I showed you what happens if we produce B, for example. Now what I want to do with you today is what happens if we have a rather complex thing. For example, we have a reaction where A is converted into B, and B then is again converted into A. So we have a reversible reaction. Before that, we only looked at an irreversible reaction where A is converted into B. There was no way back. But can we actually do something with kinetics for this reversible reaction? And the answer is yes, we can, because otherwise I wouldn't mention it. It would be pretty daft if I said, if I build up to this climax and then say, blah, 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 blah. No, you can't. So how are we going to address that? What we can do is we can try and say, right, actually we can break that down into two reactions. We can say we have a forward reaction. So a forward reaction, and that would be A is broken down into something. Let's say we have a rate constant of K1 for this. So we can write dA over dt equals minus K times A. Let's make this a first order reaction. It's just easier. So K to the power of 1. So that's the forward reaction. That's something we can very easily deal with. We can also write the same thing for the reverse reaction. Reverse. And that would be B is converted into something. Obviously, that doesn't have to have the same rate constant. We can call that, for example, K2, let's say. Yeah? Well, it's just depending on from which side you look at it. Yeah? A converted or B converted. And for that we can write dB over dt equals plus or minus. So again, it's a minus because the B is converted into something. Minus K2 times B. Again, we'll make this a first order reaction. Yeah, it makes sense so far. There's nothing terribly exciting, but it gets exciting in a minute, I promise you. So what would happen if the forward reaction was faster than the reverse reaction? So the forward reaction is faster than the reverse reaction. Well, we would lose A, and we would produce more B. But then the B reaction would kick in. And B then, we had lots of B, and B would then go back to A. So maybe they are holding the balance up to a certain point. What would happen if the forward reaction was exactly the same as the reverse reaction? So if we say forward equals reverse, what would happen? So A is converted into B, B is converted into A at the same speed, and we would reach an equilibrium. Yeah? So if you watch what's going on in your tube, you would actually see that there is no change in the concentration of A and in the concentration of B. So when we have this point reached here, this would be our equilibrium. And in the equilibrium, we would see that dA over dt equals 0. That doesn't change any longer. You still have some A left, maybe. But it doesn't change. And that's the same as dB over dt. I think I need to erase this erratic thing. Yeah? Or in other words, we have set up some equations here. So we can say, I write them on a new page, so for the forward reaction, we said minus K1 times A. For the reverse, we said that's minus K2 times B. And if they are both the same, forward and reverse reaction, we can say minus K1 times A is the same as minus K2 times B. That is when we have reached the equilibrium, when nothing changes anymore. Everything is chilled. What can we do with that? Well, actually, we can say these here are our equilibrium concentrations then. And what we do is we do a little dirty trick. I like dirty tricks. So first of all, we have a minus on both sides of the equation, so we can cancel that out. We can bring all k's to one side, and we can bring all non-k's to the other side. So, for example, we bring this K2 to that side, and we bring that to that side. So, we would have K1 over K2 equals B in the equilibrium over the concentration of A in the equilibrium. Well, just shift things to the different sides. Have you ever seen something like that? If you've done thermodynamics, have you done thermodynamics? Can you remember it? Do you love it? Who likes thermodynamics? Hands up. Whoa, not all at once, please. Is it really that bad? What's the difference between thermodynamics and kinetics? Let's start simple. What's the difference between thermodynamics and kinetics? Not in your sort of what you like, or I like thermodynamics better than kinetics. That would be absolutely devastating for me. You can't do that to me. But what's the difference between the two things? What does thermodynamics tell you? So wait a moment. You are not telling me that you have done something. How many hours? Quite a few, right? You are telling me that you have done something and you don't have a clue why you did it. Is that right? Wow! Right. Okay, let's try a different. Okay, no. Thermodynamics tells us whether a reaction could happen or not. Very simple, yeah? So if I have hydrogen and oxygen, could the reaction between them, hydrogen and oxygen, could it happen? Yes or yes? Boom! Water. Yeah? Could it happen? Yes. So that's what thermodynamics tells us. So what does kinetics tell us?
How it takes place.
How?
How it takes place.
How it takes place? Think about kinetics. How? How fast it is, exactly. Yes? So kinetics tells us not just that it could happen, it tells us how fast it happens. That's the difference between the two. Yeah? So kinetics, thermodynamics tells you that in principle we can use sugar and burn sugar, glucose, and get some energy from it. It's theoretically possible. Have you ever tried to burn sugar? No? Not really. Okay. Next time you have a lump of sugar and a lighter, try to set this sugar cube on fire. Will it work? It's a simple experiment. Anyone got a sugar cube? Anyone got a lighter? The answer is it won't work. Hang on a moment. Thermodynamics told us that it will work. So bloody liar, this thermodynamics thing. Well, actually, it does work, and it will burn very nicely, but what you need is a catalyst for that. This is where enzymes come into play, right? Bless you. Or, if you don't have an enzyme that burns the sugar, what you can do is you take some cigarette ash, put a little bit of the ash on the sugar cube, and then try to light it. Will burn. Yeah? So thermodynamics tells us that in theory it could be burned. Kinetics tells us how fast it will burn when the reaction starts. Enzymology tells us that you bloody well need an enzyme to get this thing started, or cigarette ash. So if you want to try out this experiment, get a cube of sugar, find a smoker, a lighter, cigarette, ash, and see what happens, right? So, coming back to this topic here, what you have seen before is this is just simply the equation for an equilibrium. Equilibrium. And you have seen this B over A, the concentration of B over A. And this gives you a number. What is this number called? It is the equilibrium constant. It is K EQ. And this KEQ is nothing else but the combination of these rate constants. Hey, now it comes together, huh? Quite nicely. Equilibrium is nothing, the equilibrium constant is nothing else but the rate constants. So next time you have something in the equilibrium, you know that it is just simply the ratio of the forward rate constant divided by the reverse rate constant. And I can tell you, in any cell or biochemical pathway, there are loads and loads of these equilibria present. Now, how would an equilibrium actually look like when we plot time versus A and B? So first of all, we only have A. So that would be A. We don't have any B present. But then we produce B. So it would look like that. And once the equilibrium has been formed, it would stay pretty stable. In the equilibrium, nothing happens. Equilibrium is boring. Yeah? So this phase here, this is what we call the equilibrium phase. And the two concentrations of B and A are determined by K1 and K2. This region here, where things actually do happen, what do we call that? Be creative. Be creative like a scientist. Transition, you are too creative. Called the pre-equilibrium. That's the pre-equilibrium phase. Usually, if you think about it, I said, when you've reached an equilibrium, everything is done. Equilibrium, as I said, is boring. If you have life, if you have biochemical pathways in equilibrium, nothing happens. The body is dead. The interesting part, however, that is this pre-equilibrium, when a lot of stuff is going on. And that is where biochemical pathways are usually located, in the pre-equilibrium phase. Does that make sense? Yeah? So this is a typical picture of an equilibrium reaction. Right, now let's have a look at something else. What can we do? Okay, yes, we can have a reaction where we have a reactant A, and this A is converted into B. Well, it's not terribly exciting because we've done that before. What happens, however, if B is converted into C? That is what a very common biochemical pathway looks like. So you start off with glucose, and you go all the way down the glycolysis, and you end up with, say, pyruvate. That's one enzyme reaction after the next. Yeah? So we can do that even further. And so on and so forth. You get the drift. So what happens to A? We can write dA over dt equals minus K1 times A. Let's make this, again, first-order reactions. A to the power of 1. So A is boring. It just simply goes down, as we've done that before. What happens to B? dB over dt. Well, obviously, B is produced, so B gets all the stuff that comes from A. Yeah? So therefore, we would have K1 times A. That is what B gets. Plus or minus? It must be plus, because it gets it. But at the same time, something horrible happens to B. It has to give it off again, because we have this bit here. So it is minus K2 times B. That makes sense? How would it look like if we try to draw this? So here we have our time. Here we have A and B. So A is easy, isn't it? It would go down. Like that. What happens to B? First of all, we don't have any B. That's produced from A. It would go up. Will it reach equilibrium?
Since the overt reaction is not really an equilibrium, right?
Will it reach?
It will reach.
It will reach a plateau. Will it stay there?
Yeah.
Are you sure? Johannes said it will reach a plateau and it stays there.
It will turn into C.
It will turn into C. Yeah? So this B will go up because it's produced, but then at the same time, it goes like that. It is turned into C. Yeah? So that's B. What happens to C? What would happen to C?
It goes up when B decreases.
It would, first we have no C, and it would go up like that. Yeah? And of course, if we have then further reactions like DEF, it would go like that, and we would have an F, D first. The D then would go up. So this is basically what happens in the organism constantly. If we have a limited amount of A. Actually, this is quite an interesting curve, because if you work in the pharmaceutical industry, these equations and these curves are absolutely essential for you to know. For example, what's a good example? Yeah. Men my age, they sometimes have to help nature a little bit. That's why Pfizer came up with these little blue pills. Yeah, Viagra. Great stuff. I heard, I'm not entirely sure whether this is true, that when you crush Viagra tablets and put it into water for cut flowers, you stop the flowers from wilting, so they stand up longer. But I don't know whether this is true. Flowers. But I don't want to be quoted on that. Well, you can try it out, I don't know. Anyway, let's say this is basically what happens when you take Viagra. Here you have the original product, the A, and that will be metabolized. So usually your liver will do that. It will attach something, or it will do some chemical reactions. Now then, you form a metabolite. So this B here is a metabolite of A, of the Viagra. And then this metabolite becomes further metabolized and turned into C. So the C then is another metabolite. Yeah? And so on and so forth. Now, for certain metabolites, you have to be very, very careful. Because although the original product, the A product, is non-toxic, it could very well be that one of the metabolites is toxic. The best example for that is alcohol. What happens when you drink alcohol? You get pissed. So you have something like that. What happens in your metabolism when you drink alcohol?
Becomes formaldehyde.
It's not formaldehyde, it's acetaldehyde. Yeah? So it becomes oxidized. And you have H3CCOH. What happens to that? It turns into A3CCOOH. That's right, so it turns into acetic acid. Now, alcohol per se is not terribly dangerous, so that's all right. Acetic acid is not terribly dangerous, that's all right. But the acetaldehyde that's the killer. Yeah? So this metabolite is really critical. And therefore, what you really need to do is keep the concentration of this metabolite as low as possible. Now, I show you the curves for detoxification of alcohol. So here are the concentrations. Here you have got your alcohol. Here you've got your concentration for aldehyde. And here you've got your concentration for acetic acid. This is simply because the enzyme that catalyzes this mechanism here from the acetaldehyde to the acetic acid is very efficient. So it keeps the concentration of the acetaldehyde low. Yeah, that makes sense? Haha. This is for usually Western people. What would happen if your enzyme that catalyzes the reaction from the acetaldehyde to the acetic acid doesn't work very efficiently? Again, that would be our ethanol. What would happen now with the metabolite? Our metabolite would go up. That's our ethanol. And of course, our acetic acid would only follow later. So, in this case, you have higher levels of the acetaldehyde staying there for much longer. if you have a deficiency in the enzyme that catalyzes the acetaldehyde to the acid. Can you see the difference between these two? Here you have low level. You have a low level of the acetaldehyde. In this case, you have a high level of the acetaldehyde. This is predominant in Western cultures. This here is predominantly in East Asian cultures. So if you ever went out with Japanese businessmen, you will find that they just need a sniff of cider or, micromolar amounts of vodka, and they're completely slaughtered. The reason for that is because you find that the acetaldehyde dehydrogenase, there's an isoform in predominantly Japanese and East Asian people. There's an isoform that is less active in catalyzing this reaction. As a consequence, they have higher levels of acetaldehyde, which is toxic for them. So they get immediately pissed. If you want to go on a very, very cheap date, try to find a Japanese guy or girl, because, well, hopefully they have this defective gene, and you don't have to fork out a lot. It's great stuff, right? Now, this is when we are looking at something that is in limited amount. So I said we have A to B to C and so on and so forth. But that's usually not the case when we are looking at metabolism. Metabolism usually is something is coming in. So for example, if you've got lunch, you have a constant amount of sugar coming into the system. So it would look like that. Now, if it's constant, then it's very often you can see that as almost a zero order, because something is happening constantly. Now, if we have got something like that, the whole scenario changes. For A, you would get dA over dt equals, we get K0 in, constant, but we would lose K1 times A. Let's make it easy again, first order. For dB over dt, we get plus K1A minus K2B, which is basically the same thing that we had before. And for C, it would follow. How would our reaction now look like when we plot that? A, B, time. Now, A would probably go down. So that's A. A would go down, but it would not go down completely because it's constantly delivered into the system to this K0. Yeah? What would happen to B? B would go up, and it would stay up because it gets constantly stuff from A delivered. So that's B. Remember, in this case here, we had A going down, but no new A was delivered. So B was going up and then going down because it ran out of A. In this case, B stays up. It's not going down. Have you seen something like that before? These curves. What's that? Equilibrium, isn't it? Ah. So we have sort of an equilibrium, but it's not really an equilibrium, is it? Because the B doesn't go back to A. What we have here is A to B to C to D to D, to D, to D, to D, to D. Yeah? So it's not really an equilibrium. How can we call that differently? It is an equilibrium technically. The system will be in equilibrium, but it's not really an equilibrium, and therefore it has a different name. This is called a steady state. This is what basically your organism and every single biochemical pathway goes through. They are going through steady state. And in this case, steady state is not a bad thing. In the case of an equilibrium, equilibrium is boring, nothing happens. But here, B is constantly converted to C, C is constantly converted to D, and so on and so forth. A is constantly converted to B. But the big difference here is that we have a steady production of A. It comes in all the time. Yeah? Sometimes it doesn't come in at a very constant rate. It can come in like peaks. But nevertheless, it comes in. So for example, when you just had lunch, your glucose levels will go up, massively up. Then they will go down through various mechanisms. B, C, D, E, and so on is produced, but they will never ever go down to zero. You always have a little bit of glucose left. If you are diabetic, you've got loads of glucose left. Yeah? So that's not a good thing. But it's constant delivery of A. And therefore, you have constant, and this is called flux. You have got a constant flux through the biochemical pathway. You will never run out of B or C or D or Q or S or something like that. Right? So the ideal is to keep the organism in the steady state Steady state state. Yes, it's two states. Steady state state. So that everything is nicely balanced. Now, of course, if you bring in a perturbation, if you, for example, decide that it's a great idea to eat 25 Mars bars in one go, you bring in lots of sugar. And the body needs to try and regulate that, again, through a variety of regulation mechanisms. So what could happen is that you have, let's say, A to B to C to D, and so on and so forth. And let's not forget, each of these steps is catalyzed by an enzyme. Yeah? And because you want to keep that in steady state, and you don't want the concentrations to go all over the place, like with the ethanol, what you can do, for example, is you can use one of the substances that you generate and use this as an inhibitor of the enzyme. So what would happen in this case is that your rate constant, so 1, 2, 3, K4 prime, let's call that. K4 prime would be smaller than 0. What happens if this D was actually an inhibitor of the enzyme E2? What would happen? So we get lots of A in, get lots of B in. C, we produce lots of D, lots of D, lots of D. What happens to lots of D? Lots of D inhibit the step from B to C. So we have a block there. What happens to the concentration of C in this case? Up or down? If we block this reaction here, it would go down. Yeah? Because we can't produce C anymore, we block it. What happens to the concentration of D? If C goes down, it goes down. What happens if D goes down to the inhibitor? Do we have lots of inhibitor then? No. So we lose the inhibition. What would happen in this case for the reaction from B to C? What happens in this case if there's no inhibitor left? What would happen to C, up or down? It would go up again. What happens if C goes up? What happens to D? C goes up? Sorry? D goes up. Absolutely. What happens if D goes up? What happens to C? If D goes up, C goes down. What happens if C goes down? What happens to D? D goes up. Down, sorry. Yeah, D goes down. What happens if D goes down? What happens to C? Goes up, goes up. Do you see what happens here? This D actually regulates very finely in relation to the demand. It keeps the entire pathway in a nice steady state. This is the basis of life. No regulation, no kinetics. You are royally and truly screwed. This is how life works. Any questions? Thank you very much, and I shall see you next week. Have a good weekend, and don't do anything I wouldn't do.